performing the routine project management tasks. We are inferring the various patterns in workflows based on the database of already existing tickets. So it takes a set of already created tickets inside a Jira instance. It can be 10, 100, or 200. And then it runs a set of machine learning models to infer the statistical patterns, and then helps to apply those patterns for automating the project management workflows. So what I mean by that is that we are getting a bit ahead of ourselves, but anyways, it helps with auto-assigning the tickets to the correct assignees, labeling tickets, sorting them by priorities, and all other activities related to applying various routine tasks. So for those of you who are not familiar with what a Jira app is, it's an application that is written as a service and that can be integrated with cloud version of Atlassian Jira, so that it acts as a plugin to the cloud version, showing its functionality as a small window inside the main Jira instance. And today we will talk about our experience with using Apache Ignite as a base for designing such application. And we will compare the initial legacy backend technology stack with the current stack based on Apache Ignite. And we will compare PostgreSQL plus Celery, which was the base of our stack, with Apache Ignite combined with Racer. Just a few words about Jira, why we think that it's a good idea to develop apps. It's a quite liquid market. There are a high demand for various applications. It already has data, so you do not have to do data mining. The data is already there and it's already structured, and you can use the data to do various machine learning stuff on top of it. And it can be quite profitable just because the licensing model is based on a number of users inside a single Jira instance, not a number of Jira instances served by Jira app. I already described the project, so let's just move on. So when we started this project, we had a few ideas about how our backend should look like. So these are all quite standard properties, standard wish list for a scalable distributed backend. Nothing fancy, but still it's good that we had all that in mind right from the start. But nevertheless, we decided to go with somewhat compromised solution using a not distributed backend as a starting point, just because it was simpler and allowed us to roll out releases quicker. But if we go back to the initial requirements, what we wanted ideally is being able to work to write our service inside Java and the database integrate with our Java backend web server natively. And we wanted the first-class support. We wanted highly available, horizontally scalable database, full torrent, distributed. We wanted both key value and SQL APIs. And what is somehow unusual is that we wanted to be able to run various calculations on top of that data. And keeping data safe was also critical. So we decided that transparent data encryption is a must. And finally, apart from wanting to use that backend to as a base for Jira application, we wanted to be able to deploy it on site, on premises, in case we want to serve the needs of those clients that do not want to switch to the cloud and still use Jira Server. And of course, we did not consider any solutions that were proprietary or closed source. Nevertheless, we decided to go with PostgreSQL as our first database, knowing its strong and weak sides. This is our initial technology stack. For those who are not familiar with what Celery is, so basically it's a Python-based computing grid, also known as a job queue. And the way it works, you run a number of instances of different nodes, and then you send jobs as just Python function declarations to different nodes, and then use RabbitMQ to receive the statuses and results of those calculations. So Celery requires RabbitMQ as its backend. It cannot run on its own. And initially, we had just a set of just a small set of models based on scikit-learn machine learning framework, and all those models ran on CPU. And because of that, it was quite natural to run all those inside Celery workers without having to outsource the computational load to cloud providers with GPU access. But since then, we passed the long road and had to address all those weak sides of the previous technology stack and switch to Apache Ignite. So currently, we use Apache Ignite with a combination. In combination with Spring Boot and Reserve. I will talk about Reserve a bit later. And what's important is that we use GPU-based models in PyTorch framework, and that requires to outsource certain calculation loads to the cloud where GPUs are available. So here is the current layout of our architecture. You can see here three different clouds. So this cloud is something that is managed by Atlassian. We do not control that part. These are the users of Jira, and each user is actually a separate client of Jira, and each client connects to its separate Jira instance. And inside each Jira instance, there are multiple users, like Peter did, Ilya, and other just examples. Many users inside each instance. And for us, each instance is a separate tenant. And actually, Apache Ignite is quite good solution for multi-tenancy, but still, the way it works is that we load balance the requests among Spring Boot web service, and those run background jobs. The type of jobs might differ, but the type that the most interesting is the case where we train some machine learning model. And in such cases, the payload of these requests contain a certain amount of data extracted from Jira Cloud. And this data is put inside Apache Ignite cluster, and then we run a backend computing job inside one of Apache Ignite nodes. And then it all depends on what kind of machine learning model we want to run. If this machine learning is something sophisticated, like a transformer from Hugging Face that requires GPU, then we outsource that calculation to deep learning container inside Amazon Cloud. We use SageMaker for that. So inside this container, we run various models that require GPU. If machine learning model is simpler, it's a classical ML, we just run it inside reserve node. And reserve, similarly to Celery, allows us to run arbitrary Python code inside its node. So many of you, if not all, I think know the strong sides of PostgreSQL. So I'm not going to talk too much about it. But the interesting point is that we could quite easily integrate it with Atlassian Connect Spring Boot library. What this library does, it creates a special technical auxiliary table inside the underlying database, and automatically tracks all different pieces of information related to managing connections to Jira Cloud here, like GVT tokens, names of the clients and stuff like that. And it does it automatically by hiding all the technicalities from the users of this library. And underneath, under the hood, it uses Little-based. So we could integrate it with PostgreSQL without any problems. But obviously, we wouldn't have switched to Apache Ignite if everything was good, but it wasn't. So obviously, PostgreSQL out of the box without using some other PostgreSQL-based solutions is not scalable. There are other solutions. I'm not going to talk too much about it. After the presentation, you will be able to press this links and see what solutions we considered. But on top of that, it requires a bit of effort for mapping tables to objects. We use some kind of ORM or other solutions based on PGSQL scripts, functions. It's a key value API, so it doesn't have any, and that's why it needs to be imitated. And what was critical for us is that it doesn't have any transparent data encryption integrated. There are discussions there on developer email lists about it, but it lasts for a few years, and the support is still not there. There are third-party solutions that patch PostgreSQL, but we don't consider those because they're like hacky. And we also need it in memory tables, but in PostgreSQL, you cannot have one unless you try to allocate a table space in a RAM disk on Linux or use unlock table. But all those are not true in memory tables. In the first case, it exposes your cluster, PostgreSQL cluster, to crashes, basically compromising the consistency. In the second case, you just disable write-ahead log, which is not the same as having a full in-memory table. So if we compare that to Apache Ignite, so as you well know, it solves some of those problems. It's distributed, scalable. It has support for key value API, but nevertheless, not everything was good. Here are the problems we faced. So one of those is that we couldn't find any open source solution for data migration and schema version tracking. So we had to implement the one by ourselves, and we plan to open source it. Of course, it doesn't solve the whole problem for all possible cases, but for our case, it works. And basically, the second problem is a result of the first one. It is difficult to make backups and migrate data to new versions of the product, because our schema isn't static. We change it, and when you change schema, you need to migrate your data from the whole cluster to the new version. We know that in the last version of Apache Ignite, there is a limited support, but since we use TDE, transparent data encryption, we cannot use that feature because in Apache Ignite 2.9, snapshots are not available for TDE enabled encrypted caches. Also, no referential integrity, which was upsetting, but we could live with it. But as a result, no foreign keys and no other nice features of SQL, like window functions and stuff like that. So the SQL support is quite limited. No transactions that are production ready. We also struggled with using Spring Boot DevTools. So what we did, we changed our developers change the objects that we store inside database. And if you do not take certain measures, then it breaks the communication with the cluster. And the way we solve that is we are placing all the files, all the classes that we store inside database in a separate jar file. And we place that jar file on each of the nodes. And this way it works. We know that Apache Ignite has a certain way of preventing problems when multiple developers in the same network try to use Apache Ignite. It's called static IP resolution protocol, but we found it not very useful for our case because we wanted to be able to experiment inside each of the developer machines with a full set of features, including multicast IP resolution. And that's why we had to implement the IP tables, apply IP table configuration on each of the machines. We use Linux. And so it was not very difficult, but still, this is something that you need to keep in mind. Otherwise, as a developer, one of the developers, if we're not careful, can break everything on other machines because his node, her node becomes discoverable. Also, since our machine learning models, the Python-based, we could benefit from having transactions inside PostgreSQL, but there is no any support for that, and that is upsetting. So the way we solved that, we do not need that right now because we switched to Reserve, and I explain why we do not need that anymore. But previously, when we used Celery, we had to run Python Java bridge called Py4G. This is a project that is used also by PySpark, and it allows to have a full featured API for Python via bridging Java API through this Py4G. Finally, we use Atlassian Connect Spring Boot, and it ships with Spring 5, while Apache Ignite has Spring 4 as a dependency. And we found a way to work around that via placing the dependency on Spring 5 prior to Apache Ignite dependency, and it worked. So what was good with Celery as a computational grid is that we could run arbitrary Python code. So regardless whether it's just a machine learning model, it was machine learning framework agnostic. No depends on whether it's a PyTorch or TensorFlow or MXNet, doesn't matter. And we also had strong delivery guarantees because Celery used RabbitMQ message broker under the hood. But again, Celery does have its weak sides. What we did not like is that Celery requires an external message broker, and we in the developer mode, when we developed on our machines, we had to run RabbitMQ instance as a separate container, Docker container. What we also did not like is that unless you use Kubernetes, and for development purposes, we use just Docker Compose, and Kubernetes is only for testing on our staging environment and for the cloud. But on developer machines, we do not use something like Minikube, we just use Docker Compose. And in such cases, there is no any support for automatic failover in case one of the RabbitMQ nodes goes offline. And so we had to implement that. Also, Celery being a pure Python-based framework doesn't have a very convenient set of Java API interfaces. Its protocol is known. You know what kind of JSON should be sent to RabbitMQ to start the job, to stop the job, to set signals, but it all somehow hacky. So it wasn't a pleasant experience. So when we switched to Apache Ignite, we decided why not start using its computing capabilities. Yes, we could still stick to Celery, and we did so for some time. But since we already have this feature, why not use it? So we started using it and discovered that it has somehow weaker delivery guarantees. What we could understand based on the discussions in the developer mailing lists is that in case Apache Ignite node goes offline, the node that runs the job to which the message is sent, the message can be lost. So it's a big weaker guarantee comparing to what RabbitMQ provides here, because RabbitMQ guarantees that at least once you deliver the message, but this is not the case for Apache Ignite messaging protocol. Also, again, we did not have transactions inside Python, and that's why we had to struggle with using Python to Java bridge. It's one more component, so many moving pieces inside the system, not good. So let me summarize the difficulties we had when we started and proceeded with switching from PostgreSQL to Apache Ignite, and switching from Celery as a computing grid to Apache Ignite as a computing grid. So obviously we had two components we had to replace. We had to replace the database by switching from PostgreSQL to Apache Ignite, and we had to replace the computing grid. So if, but in a real project, you do not try to replace too many pieces at once. So what we did, we just replaced the PostgreSQL first and kept Celery. But again, cannot use transactions inside Python. That's why still had to use this bridge. But then one of the most confusing difficulties that we struggled a bit with was the problem with Atlassian Connect Spring Boot library. So this library, as I mentioned before, uses Liquibase under the hood, and this Liquibase creates a table called Atlassian host. This is the auxiliary table managed by this library. If it doesn't exist, but in our case, JDBC driver for Apache Ignite did not provide the full SQL support needed for Liquibase, and that is why this library couldn't create this table. So what we did, we created a separate container that ran inside Kubernetes in production as a Kubernetes job. And the job of this container was to use query entity API to create this table so that it is visible to this library as a SQL table. And then Liquibase just looked at inside Apache and said, okay, I see this table, no need to create it. And that it just proceeded to the next step, and everything worked. But it took a while to figure how to work around this. Again, still not clear why Apache Ignite ships with Spring 4. So a little bit of attention is needed if you need Spring 5. What was confusing is inability to debug things by looking inside a database inside Apache Ignite cluster and see what's going on a field level. We had two types of fields. One type are fields of simple types like string, integer, and those fields were perfectly visible in tools like dbeaver or DataGrid. But we had a second set of tables that were represented by complex types. And we had to implement manual serialization to readable XML to be able to look inside those tables and see the content of these columns. And otherwise, it was just some binary stuff there, not readable, very difficult to debug. And finally, the final problem is related to our tool we developed for producing the backups of the database. So the way we do this is via scanning the whole cluster and storing the content of each cache into a set of arrow files. So it's a row-based data format. And the problem is that we make a heavy use of atomics inside Apache Ignite to be able to globally assign identifiers to different business objects. For example, to tenants. When a new client buys our application, we need to register it and assign a new tenant ID. And for that purpose, we use those atomics. But it's just an example. There are many of those atomics there. And when we back our cluster up, we want to store all those atomics next to the data. But the problem is that Apache Ignite does not provide any way of getting the list of atomics inside the cluster. So currently, we just have to hard code those inside the external tool that backs up the database. We know that there are metrics inside Apache Ignite that allow to query certain statistics from the cluster, but unfortunately, the list of atomics is not among those. But another interesting point is that by replacing Celery combined with PostgreSQL with Apache Ignite, we also basically replaced the computational grid. But the problem is that we still had Python-based models. We needed some place to run those in. And we investigated a few possibilities. We considered using the machine learning capabilities of Apache Ignite, but the problem is that Apache Ignite concentrate mostly on classical ML that is run on distributed data. But in our case, we heavily use deep learning models, complex models. And those models are far ahead of what Apache Ignite has integrated. And that is why we decided that we just needed to have computational grid that can run arbitrary Python code by providing both GPU and CPU calculation capabilities. So we went with Reserve, but the question is, how do you integrate Reserve with Apache Ignite? And the second question is, if Apache Ignite provides weaker delivery guarantees, how do you manage those cases when the message is not delivered? So the second problem has a simple solution. Since we do not run a serious financial application, we just inform the client that something went wrong, and the client presses the button one more time. So the first problem also solved by running a separate service based on a combination of Reserve containers. So as I said before, we run Reserve as a combination of nodes, and inside of each Reserve node represented by a Reserve container, we run scikit-learn based set of models. We run machine learning endpoint based on REST API, and we run SageMaker Python client. So when Apache Ignite node receives a job, it forwards this job to Reserve, unless this is some kind of not ML related job. Then Apache Ignite just calculates everything by itself. So the examples of such jobs are jobs related to business logic. If you just need to process data stored inside Apache Ignite cluster, you do not need ML. So this job run inside Apache cluster with its computing API is a perfect place. And you do not need any external solution. But if it's ML, then if it's a simple model, again, depends on many factors, amount of data, kind of a business logic request that client sends. You decide if you need deep learning, you go to deep learning container. So this set of containers run inside Amazon Cloud, and those are available via SageMaker REST API. If the machine learning task is simpler and does not require GPU, we just run that inside the same cluster where Apache Ignite runs. But again, inside Reserve container. I guess after the presentation, you will be able to go through the references if you want. We try to back our judgments up by carefully selected links so that we do not try to say something that just our opinion. We try to base our opinion on the results that other people were able to reproduce. It's time to ask questions, I guess.
Yes, and we already have two in our chat, and let me please read them for our viewers. Do you copy data from an Ignite node to Reserve node before running the ML jobs? If yes, are those nodes hosted on the same machine?
We just send data via REST API as a payload. So yes, we copy data because we decided that we just do not use Python API right now. We just use REST API, just simple solution. If at some point we see that the amount of data transferred between Apache Ignite calculation job and Reserve is becomes a bottleneck. So if it stops or slows down things, then we act. Hopefully by the time we will be able to benefit from better support at Python API level from Apache Ignite. and implement more sophisticated stuff than just fetching data from Apache Ignite via Python API. Right now, it's just possible to extract value by key and run a simple SQL request. That's it.
Mm-hmm. Also, I see here a note about Spring 5. Apache Ignite supports Spring 5 fully. It's just default to Spring 4. Says, yeah. So any comments on that?
I think I agree with that statement. So yes, it just was confusing that the default is Spring 4, and that's it. But
Okay.
yes, it works with Spring 5. Yes.
Did you have any issues with TDE feature? Do you have any feature requests for TDE? That's the developer's question.
Yes, yes, sure. We want to be able to use the latest feature of snapshotting with TDE enabled, because right now the feature of generating snapshots of Apache Ignite cluster is not supported for encrypted caches, and it's a major upsetting factor and stopping us from using that snapshotting capability of Apache Ignite.
The next question, can you share your opinion about what would be the best procedure of creating, restoring cluster backups from your point of view?
I think that it would be good to have a few options, but in our case, I can only say what would be the best for our case. For our case, we need the readable Ignite independent data format to which data is serialized from Apache Ignite cluster 2, which have chosen Avro data format. But it doesn't have to be Avro, but it needs to be some data format that you can work with without using Apache Ignite, with which you can work with using some third-party libraries for Avro, or if it's a Parquet file, and via Parquet API, but Parquet is a columnar based format, so it cannot be most likely Parquet. But I guess it doesn't matter much what kind of data format it is. What matters is that this format needs to be easily parsable by external tools independent of Apache Ignite. Then, if it is the case, then you can write patches that work on data and schema outside of Apache Ignite. So this is what we did. Once we have the data serialized from Apache Ignite as a set of Avro files, we just write patches. For instance, patch that upgrades data and schema from version 0 to 1. Then the second patch from 1 to version 2. So each of those patches is just a simple Java program. And what this patch does, this program does, just reads a set of Avro files, transforms data in those, and stores the transformed data back to the disk as a set of Avro files. Of course, I could only assume that this strategy is not applicable as well to large data sets, but in our case, it works.
Thank you. So guys, you also can just unmute yourself and ask a question if you like.
Yeah, I have a couple of questions. Thanks, Peter, for presenting. It was interesting to learn, and I think that I saw many community members on the line. So hopefully they will take your feedback and improve Ignite with the next versions. Speaking about machine learning, you mentioned that you're running some deep learning related tasks, but have you tried to use Ignite ML Java APIs? Like, if yes, then what's your thinking?
So here's the problem. We run a sophisticated machine learning pipelines for natural language processing. So it is quite different from what Apache Ignite provides, unfortunately. So the most complex deep learning model that Apache Ignite provides is a multi-layer perceptron, which is just a fully connected multi-layer deep neural network, but it's just a simple case. It's a kindergarten model in terms of complexity of what state-of-the-art machine learning models that use deep learning are like. So that is why I can see two ways. Either Apache Ignite tries to implement every possible deep learning model accessible from Java, or Apache Ignite tries to integrate with the most popular language in the world used for machine learning. So as a user of Apache, of both Python, as a machine learning enthusiast, and Java development at the same time, what I would like to have in Apache Ignite is that Python becomes a first-class citizen, and that Apache Ignite provides better integration, so that you can write just pieces of Python-based code that implement those models externally to Apache Ignite, so that Apache Ignite doesn't try to be better than the rest of the machine learning world. But I'm not trying to offend Apache Ignite, because it has its strong sides as well. Because obviously, if you have a lot of data, many terabytes stored inside the cluster, and you want to run to a set of classical ML tasks on top of that data, then no need to use external machine learning frameworks. And Apache Ignite is perfect for that. But what do you do if you just need to take a small subset of data stored inside Apache Ignite, like a set of Jira tickets for that particular client? For instance, it can just be a couple of thousand tickets, and run a complex machine learning pipeline on top of that. It can be a combination of some kind of transformer-based model, SciPy, and stuff like that. Just a couple of examples, but there are numerous number of libraries for machine learning, for NLP. And people that design those models usually do not know Java. And even if Apache Ignite supported, let us imagine that one day Apache Ignite supports transformers, but it's difficult to be ahead of the rest of machine learning community in terms of having support for the state-of-the-art model. For instance, if the library called Hugging Face transformers support some kind of the new model that Google developed 3 months ago, and it has implementation in either TensorFlow, JAX, or PyTorch, or I don't know, maybe Julia. It doesn't matter. Apache Ignite just won't be able to react immediately by implementing that model. But if it had integration with Python, no problem. It could benefit from running that model. But right now, since there is no such capability of running machine learning model that are Python-based inside Apache Ignite cluster, we had to implement a separate solution. Maybe that's not bad. I guess that's not for me to decide.
Ivan, I suppose that you have some updates here.
Sure. Thank you. Thank you for inviting me.
Thanks a lot for your presentation.